Cell 1. In this cell, we're diving into FRED, which stands for the Federal Reserve Economic Data. FRED is an invaluable resource that provides access to an extensive collection of economic data, allowing users to analyze and visualize trends that can inform their decision-making. This platform offers tens of thousands of time series data points from a wide range of sources, both public and private, which can significantly enhance our understanding of economic conditions. The overview presents several economic indicators available through FRED, such as the Consumer Price Index, which signals inflation pressure, and unemployment metrics that highlight labor market stress. By examining these indicators, analysts can glean insights into the current economic landscape and anticipate future trends. For example, claims data can serve as an early signal of recession, while retail sales figures can gauge consumer demand, helping businesses strategize effectively. Sentiment data, on the other hand, reflects forward expectations about economic conditions, giving stakeholders a way to navigate uncertainty. The cell also outlines various applications for this data, which include recession probability models, GDP nowcasting, market regime detection, and shifts in investment allocations. These applications underscore the practicality of FRED in both academic research and real-world financial decision-making. As we look ahead, the following cell will likely expand on how to effectively utilize FRED's tools and understand the specific datasets within the platform, ensuring that we can truly harness the power of this resource for comprehensive economic analysis. Cell 2. In this cell, we're laying the foundation for analyzing significant economic indicators using data sourced from the Federal Reserve Economic Data, or FRED. This is crucial because understanding these indicators helps us gauge the health of the economy and make informed decisions in various fields, such as finance, policymaking, and business strategy. We begin by establishing a dictionary that maps key economic indicators to their respective FRED series codes. This includes essential data on inflation, labor statistics, and consumer behavior that will form the core of our analysis. We also set a starting date for our data collection and leave the end date flexible to retrieve the most current data available. Next, we implement a helper function to fetch data from FRED. This function takes our predefined series map and the specified date range, allowing us to efficiently gather all relevant data into a single data frame. With this structure in place, we can easily manage and process the multiple series we're interested in. Following the data retrieval, we roll the data to a month-end frequency using another helper function. This step is essential for ensuring that all data points correspond to the last observation of each month, which helps us maintain clarity in our time series analysis and smoothens any irregularities that might arise from different frequencies of data collection. To enhance our analysis further, we derive additional features that reflect inflation rates, retail growth, and labor market momentum. For instance, we calculate year-over-year and month-over-month percentage changes for both CPI and retail sales. These derived metrics help us better understand trends and provide insights into economic movements. A notable aspect of our approach is how we handle missing data. If certain series are unavailable, we implement fallback strategies, such as using nominal retail sales adjusted for inflation when real retail sales data is missing. This kind of thoughtful engineering helps make our analysis robust and adaptable. The cell concludes by displaying the shape of the raw data and the processed month-end data, giving us a clear indication of our dataset's structure. With all of our indicators prepared and enriched, we are now ready to dive deeper into analyzing economic trends. The next cell likely focuses on visualizing these indicators to provide intuitive insights that upgrade our analysis to a more actionable level. Cell 3. In this cell, we're setting the stage for our analysis on corporate hiring decisions by gathering and preparing macroeconomic data that influences these choices. This is crucial because understanding the environment in which companies operate can illuminate patterns and trends in hiring. We begin by importing the necessary libraries, such as NumPy and Pandas for data manipulation, as well as Plotly for visualization. Notably, we employ Pandas Data Reader to fetch data from the Federal Reserve Economic Data API, a vital resource for economic indicators. As we look to gather data, we've identified key economic indicators, each assigned to a variable in our series dictionary. These indicators, including the unemployment rate and consumer sentiment, are monthly metrics that can influence hiring trends. The function to month end plays an important role in transforming our data for analysis. It ensures we handle our time series correctly by rolling weekly data into monthly averages or taking the last observation of the month, depending on the type of data. This information is vital for ensuring consistency in our analysis. Next, the load Fred series function fetches the raw data and assembles it into a dictionary that organizes the various economic indicators. By iterating through this dictionary, we create a structured dataset that is representative of the current economic climate. Once the data is loaded, we prepare it by applying the to-month-end function to each economic indicator, transforming them into a uniform monthly format. At this stage, we concatenate all the series into a single data frame, renaming the columns for clarity. Importantly, we also remove any entries with missing values, which can skew our analysis later on. Finally, to verify our work, we print the shape of the resulting data frame and display its first and last few records. This step is essential for ensuring that the data is structured correctly before we move on to our predictions of hiring trends. In the next cell, we'll likely delve deeper into building predictive models using this meticulously prepared data, searching for relationships that can enhance our understanding of corporate hiring decisions. Cell 4. In this cell, we're setting up a framework for forecasting future hiring trends by integrating macroeconomic features. This process is crucial because it allows us to better understand the dynamics that influence employment growth over time, particularly in relation to broader economic indicators. First, the focus is on calculating a target variable, which is the 3-month ahead change in payroll employment. This target, represented as a percentage change, helps us capture the hiring momentum by looking at how employment fluctuates monthly. We're creating a new column in our data frame to hold this information, ensuring it's shifted appropriately to align with the forecast period. Next, we delve into feature engineering, which is about deriving additional metrics that can give more context to our predictions. For instance, we're examining changes in the unemployment rate, weekly jobless claims, and various retail and industrial production indices. By measuring these changes over specific periods, like 3 months and 1 year, we generate insightful metrics that reflect the economic environment's influence on hiring. An important step follows, where we introduce lagged features. This means we're integrating the past values of our indicators to mitigate the risk of instantaneous bias that could distort our results. By shifting these variables by 1, 2, and 3 months, we can account for the delayed effects that macroeconomic shifts have on hiring behavior. Once these features are constructed, we extract the relevant columns needed for our model. At this point, we're also cleaning our data to remove any rows with missing values, ensuring a more robust dataset for analysis. The output consists of matrices X and Y, which represent our predictors and target variable, respectively. This entire setup not only prepares us for effective modeling later, but also lays a solid foundation for understanding how past trends might influence future hiring. As we transition to the next cell, we'll likely focus on developing a predictive model using these features, allowing us to distill insights from the data and potentially forecast future employment dynamics more accurately. Cell 5. In this cell, we're implementing a time-based train test split on our dataset as we prepare to fit a predictive model. The rationale behind opting for a time-based approach is crucial. It allows us to simulate how the model would perform on unseen data, reflecting real-world scenarios where predictions must be made on future observations. First, we identify the split point by calculating 80% of the total data size, meaning that our training dataset will capture the earlier chronological patterns, while the remaining 20% serves as our test set for validation. This division is critical, especially in time series forecasting, where earlier data provides context for future predictions. Next, we separate our features and target variables. The training dataset containing 80% of the data is used to fit our model, while the testing dataset consists of the most recent 20%, allowing us to assess the model's performance based on how well it predicts this unseen data. We then create a random forest regressor model, specifying several parameters, such as the number of estimators, which is set to 600 for robust performance, and constraints on tree depth and minimum samples per leaf to prevent overfitting. By fitting the model to our training data, we're teaching it to recognize patterns and make predictions. After it's trained, we go ahead to make predictions on both the training and test sets. This helps us evaluate how well our model is generalizing. To truly gauge its performance, we compute the mean absolute error for both sets. Finally, we output these errors to compare the model's predictive accuracy on the training data versus the test data. Will serve as a benchmark for future improvements. It's essential to be wary of overfitting, particularly with the training error, as a significant discrepancy between the train and test metrics can signal that the model has picked up noise rather than essential patterns. Looking ahead, the next cell will build on this analysis, likely by delving deeper into performance evaluation, exploring additional metrics, or even refining our model based on these insights. Cell 6. This cell is focused on visualizing the relationship between predicted and actual values for a corporate hiring forecast, specifically looking at the 3-month ahead payroll growth data. Effective data visualization is crucial in understanding how accurate our predictions are compared to actual outcomes, and this plot will help illuminate that relationship clearly. The first part of the code creates a data frame that organizes our data in a structured way. It combines the dates from our test dataset with the actual values and predicted values for 3-month ahead payroll growth, allowing us to have a coherent dataset that we can draw insights from. By setting the date as the index, we can easily reference time points later in our visualizations. Next, we utilize Plotly, a powerful library for creating interactive visualizations. A figure is initialized to serve as a canvas for our plots. We add 2 traces to this figure. One represents the actual values, while the other showcases our predictions. This dual representation allows for direct comparison, making it easy to spot where the forecast aligns with reality and where it diverges. The graph's layout is carefully crafted to enhance readability and comprehension. It includes a title that clearly explains what's being depicted, along with labeled axes to indicate the timeline and the metrics being measured. The dimensions of the figure are set to provide ample space for the data to be displayed clearly, enhancing the viewer's experience. It's important to note that while we aim for an accurate portrayal of trends, various assumptions can affect the results, such as data integrity and model reliability. As with any predictive analysis, while we might see strong correlations, they do not necessarily imply causation. Moving forward, the next cell will likely dive deeper into interpreting the implications of this visualization. We may discuss how well our model performed in more detail, or explore alternative forecasting methods. This step is vital for enhancing our understanding and improving future predictive accuracy. Cell 7. This cell focuses on visualizing feature importance in the context of our hiring forecast model. Understanding which variables contribute most significantly to our predictions is crucial for interpreting the model and making informed decisions. Here, we utilize a bar plot from Plotly to illustrate the top 15 features, revealing the factors that drive our hiring predictions. The first step involves creating a series object that captures the feature importances derived from our model. These importances quantify the contribution of each feature in predicting the hiring outcomes. We're particularly interested in sorting these values in descending order, which allows us to highlight the most impactful variables. After we sort the series, we take the top 15 features that stand out the most. Next, we convert this series into a data frame for easier manipulation and clarity in our visual representation. We reset the index and rename the columns to feature and importance, making it straightforward to interpret in our plot. The bar plot itself is oriented horizontally, providing a clear view of which features have the highest importance scores. This orientation often enhances readability, especially when feature names are longer. Once the visualization is set up, we customize its dimensions for optimal viewing and then display the figure. It's important to be mindful that while feature importance helps us understand our model, it doesn't imply causation. The importance scores reflect the contribution of features, but we should be cautious about drawing definitive conclusions without further analysis. As we move into the next cell, we will likely build upon these insights by exploring how these key features manifest in our actual hiring forecasts. This will help us validate our assumptions and refine our strategy moving forward. Cell 8. In this cell, we're establishing a straightforward decision-making framework that uses predicted payroll growth to guide hiring actions. By setting specific thresholds, we can determine the right course of action based on forecasts, which is crucial for organizations when navigating potential economic changes. The function defined here, called hiring action, evaluates the predicted payroll month-over-month increase 3 months into the future. Essentially, if the forecast indicates a significant growth of at least 0.20%, the recommendation is to hire, expand. This suggests a robust economic environment, encouraging investment in staffing. Conversely, if the prediction hovers closer to 0.03% or below, implying stagnation or potential decline, the function advises a freeze, caution approach. So, in this scenario, the organization would want to hold off on hiring until conditions improve. Any predictions falling in between these thresholds will result in a normal recommendation, suggesting that the current state can continue, but without major expansions or cutbacks. In the next steps, we're creating a data frame called Decisions that replicates the data from PredDF, a previous output containing our predictions. Here we apply the hiring action function to our predicted payroll values, generating a new column dedicated to the proposed actions. This will provide us with clarity on how our hiring strategy should adapt based on our macroeconomic forecast. To visualize these hiring actions over time, we generate a scatter plot that maps the prediction values across different dates, color-coded according to the suggested actions. The plot's hover feature enriches the data experience, revealing actual payroll growth alongside our predictions. This allows for a nuanced analysis of how closely our forecasts align with reality. Moving forward, we'll likely delve deeper into interpreting these visual results and examining how effective our hiring decisions have been relative to economic outcomes. This will be vital for refining our approach in future analyses. Cell 9. In this cell, we are preparing to analyze some key economic indicators that play a crucial role in understanding the performance of an economy. By examining metrics such as the unemployment rate, initial jobless claims, retail sales, consumer sentiment, and industrial production, we can gain valuable insights into economic trends and consumer behavior. The unemployment rate reflects the proportion of the labor force that is jobless but actively seeking employment, while initial jobless claims provide a glimpse into the number of people filing for unemployment benefits, serving as a leading indicator of the job market's health. Retail sales indicate consumer spending, which is vital for economic growth, revealing how much money is being exchanged in the economy. Consumer sentiment, on the other hand, assesses how optimistic or pessimistic consumers feel about their financial situation and the economy as a whole. Lastly, industrial production measures the output of the manufacturing, mining, and utilities sectors, giving us an idea of overall economic productivity. As we analyze these indicators, it's essential to think about how they interconnect and influence one another. For instance, a rise in retail sales could suggest a strong consumer sentiment, signaling a healthy economy, which in turn may lead to a decrease in the unemployment rate. Conversely, high unemployment may cause consumer sentiment to dip, affecting retail sales negatively. However, as we proceed, we need to be cautious of potential pitfalls, such as assuming that these indicators always correlate directly, or interpreting them in isolation. In the next cell, we will likely take steps to visualize these relationships, allowing us to discern patterns more clearly and make more informed interpretations. This visual representation will deepen our understanding of how these economic inputs interact over time, setting us up for more complex analyses ahead. Cell 10. In this cell, we're diving into the crucial task of retail sales forecasting, which is essential for businesses to make informed decisions regarding inventory and resource allocation. We start by preparing our data, importing various economic indicators that will help us gain insights into retail sales trends over time. The logic here revolves around collecting and processing data from multiple sources. We utilize a dictionary to map various indicators, such as real retail sales, unemployment rates, and consumer sentiment, each identified by a corresponding code. This organization makes it easier to manage and retrieve the data we need. Notably, we're using the Pandas Data Reader library to fetch this data from the Federal Reserve Economic Data, or FRED, which ensures we're working with reliable and timely information. We also define a function, toMonthEnd, that converts our data into a monthly format. It can take either the last available data point or the average for weekly data, like initial claims for unemployment, which is important for making sure our comparisons are meaningful. After loading our raw data, we apply this function to each of our indicators to ensure they are all aligned temporally, which is essential for building a coherent forecasting model. The resulting data frame combines all these economic indicators, filtering out any incomplete entries to maintain data quality. This structured dataset will be the foundation for further statistical analysis and modeling. The output, displayed at the end, gives a quick look into the initial and final entries of our processed data, revealing just how much we've gathered and how it looks. Looking ahead, we will likely build statistical models to analyze this data and predict future trends in retail sales using techniques such as regression analysis. The groundwork we've laid here, with clean aggregated data, sets us up for that next step into predictive analytics. Cell 11. In this cell, we're focusing on creating a target for predicting future year-over-year growth in real retail sales, while also incorporating macroeconomic features that could influence this growth. This is essential for understanding not just current market conditions, but also forecasting trends that can significantly impact economic decision-making. We begin by copying the existing dataset, ensuring we preserve the original data while manipulating this new version. The first step is calculating the year-over-year growth in real retail sales by using the percentage change function, specifically targeting retail sales data over a 12-month period. This allows us to capture any seasonal fluctuations in retail sales that may occur year after year. Next, we introduce various macroeconomic indicators as features to help predict the retail sales growth. These indicators include the percentage change in payroll employment, the change in the unemployment rate over 3 months, and similar calculations for claims, consumer price index, federal funds rate, and industrial production. Again, applying a combination of percentage changes and absolute changes to create a comprehensive set of insights. Moreover, we recognize that some indicators may have a lagging effect on retail sales. To account for this, we generate lagged variables for each of our key features at different time intervals, namely 1, 2, 3, and 6 months. This addition allows us to see how past values of these indicators have influenced retail sales growth, thus enriching our predictive modeling. After creating these lagged columns, we also ensure data cleanliness by dropping any rows that contain null values in our newly developed feature columns or in our target variable. This will help maintain the integrity of our dataset for analysis. As we reach the end of this cell, we take a quick look at the last 5 entries of our data to verify that our calculations have been executed correctly, specifically observing the fields related to real retail sales and its growth. Lastly, we print out the count of our feature columns, giving us clarity about how many predictors we have at our dispersal. Looking ahead, this groundwork sets the stage for the next cell, where we will likely dive into model training using these carefully crafted features to better understand the dynamics at play in predicting retail sales growth. Cell 12. In this cell, we're diving into multi-horizon forecasting by utilizing direct models to predict retail year-on-year growth for 1, 3, and 6 months ahead. This approach allows us to assess how well our models perform over different timeframes, which is essential for making informed business decisions. The process begins by defining our horizons, those key time intervals for which we want predictions. Inside a loop, we iterate through each horizon, creating a temporary data frame that holds our original data, but augmented with a new column representing future values of retail growth, specifically shifted to account for our forecasting goal. It's crucial to handle any missing values effectively, so we drop any rows that don't contain these future values, ensuring that our dataset remains clean and usable. Next, we separate our features and target variable, preparing for model training. Here, we apply a standard data splitting technique to partition our data into training and testing sets, with the first 80% dedicated to training. This ensures that our model learns effectively before we test its performance on unseen data. We then clone our base model, a random forest regressor configured with specific parameters that govern its learning behavior, such as the number of trees and the depth of each tree. After fitting the model to our training data, we use it to make predictions on the test set. This results in predictions for future growth rates, which we then evaluate for accuracy using metrics like mean absolute error and R-squared values. It's worth noting that the choice of models and parameters can significantly influence performance, and there can be assumptions about the underlying data distribution that should be considered. Each prediction is stored alongside actual values, contributing to a comprehensive view of the model's effectiveness. By the end of this cell, we've compiled a summary data frame that outlines the performance metrics for each horizon, giving us a clear picture of the model's strengths and weaknesses. Additionally, a consolidated data frame captures all predictions across the various horizons. Looking ahead, the next cell will likely explore how these insights can be visualized or interpreted further, allowing us to gain even deeper understanding from the forecasting results. This will be instrumental in guiding strategic decisions moving forward. Cell 13. In this cell, we're creating several visualizations using Plotly to interpret and analyze our retail sales forecasting results, which is crucial for gaining insights into our model's performance and the factors influencing predictions. The first plot is a line chart that allows us to observe the actual versus predicted retail sales growth over time, separated by different forecasting horizons. This not only presents the trends, but also highlights how the predictions stack up against reality, making it easier to identify patterns. Next, the scatter plot provides another layer of analysis by comparing actual versus predicted values directly. This visualization is colored by the forecast horizon and includes a trend line, which helps assess the overall prediction quality and visually identify any discrepancies. Observing these correlations helps us understand whether our model is performing well or if there are specific areas where it misses the mark. As we delve deeper, the cell then extracts feature importance from our model, specifically looking at the third month's predictions. By creating a horizontal bar chart that showcases the top drivers of retail growth forecasts, we gain clarity on which variables have the most significant impact on our predictions. This step is crucial for both improving our model and guiding future decisions, as understanding the most influential features can shape our data collection and modeling strategies. Throughout this process, it's important to notice assumptions around the data and what these visualizations represent. For instance, the accuracy of the predictions heavily relies on the underlying data quality and the model's training. Keeping an eye out for potential pitfalls, like overfitting or underfitting, is essential to ensure the model and the interpretations drawn from it are valid. Moving forward, the next cell will likely build on these visualizations by incorporating insights gleaned from the feature importance analysis and potentially adjusting our model or forecasting methods based on these findings. This continuous feedback loop will enhance the accuracy and reliability of our retail sales forecasts. Cell 14. In this cell, we are creating a decision signal for our retail plan based on predicted year-over-year growth rates. This is crucial because it informs our operational strategies, allowing us to adapt inventory levels, promotional budgets, and staffing according to anticipated demand. The first step involves isolating a subset of our predictions, specifically looking at a 3-month horizon. This timeframe is relevant because it strikes a balance between being timely and actionable. By copying this subset and setting the date as the index, we prepare our data for analysis. Next, we define a function named plan bucket, which evaluates predicted growth rates to categorize them into 3 operational strategies: expand, normal, and conserve. If the predicted growth is at least 3%, we interpret this as a signal to expand operations, meaning we'd likely increase inventory, allocate a larger budget for promotions, and potentially hire more staff to meet expected demand. On the other hand, if the growth is 0 or negative, we consider demand to be weakening, prompting us to conserve resources by reducing purchases and tightening labor budgets. For anything in between, we settle for a normal strategy, maintaining current operations without any drastic changes. After applying this function to our predictions, we generate a scatterplot using Plotly Express. This visual representation captures the relationship between date and predicted growth, while coloring the points by the operational strategy, which provides instant clarity on how our plans align with market expectations. A hover feature also allows us to see actual sales figures, adding another layer of insight. Finally, we display the last 10 entries of our modified data frame to review how the planned categories are distributed against our predictions. The careful structuring here sets the stage for further analysis. In the next cell, we will likely explore the impact of these decisions on operational outcomes or analyze historical data to inform our future predictions. Cell 15. In this cell, we're preparing to delve into key macroeconomic drivers that significantly influence economic health and decision-making. Understanding these concepts is essential because they offer insight into how various factors can affect markets, consumer behavior, and overall economic stability. We start with the Consumer Price Index, or CPI, which serves as a primary measure of inflation. It tracks the changes in the price level of a basket of consumer goods and services, providing crucial information about purchasing power. Next, we consider real income, which adjusts nominal income for inflation, reflecting what consumers can actually afford. This is vital for assessing economic well-being. Consumer sentiment follows, which gauges how optimistic or pessimistic individuals are regarding their financial situation and the overall economy. High consumer confidence can spur spending, driving economic growth, while low sentiment may have the opposite effect. Unemployment rates are also critical, as they indicate the percentage of the labor force that is jobless and actively seeking employment. This metric can reveal underlying economic issues or recovery trends. Finally, we look at interest rates, which impact borrowing costs. Lower rates can encourage spending and investment, while higher rates may stifle economic activity through increased costs of loans. Each of these drivers interlink, creating a complex web of influence that shapes economic policies and consumer choices. As we transition to the next cell, we will likely apply these concepts to analyze current economic conditions, allowing us to synthesize this foundational knowledge into practical examples. This forward momentum will help us deepen our understanding of the economic landscape we're examining. Cell 16. In this cell, we're diving into feature engineering, specifically focusing on creating valuable monthly indicators that are crucial for modeling recessions. These features will help us better understand macroeconomic conditions by analyzing various economic signals, such as the slope of the yield curve and year-over-year changes in key metrics like activity and inflation. To achieve this, We start by importing necessary libraries for data manipulation and analysis. The code sets up a time range starting from January 1st, 2000, to the present. Within this defined period, we identify several key economic series that will serve as both predictors and targets in our model, including unemployment rates and consumer sentiment, among others. Each series is paired with a corresponding identifier for clarity. The heart of our feature creation lies in the to-month-end function, which standardizes our data to ensure that all observations align with the end of the month. This function handles missing values and aggregates data appropriately, averaging weekly figures for initial claims while taking the last available observation for other series. It's essential to note that the choice of aggregation method can impact our insights, so understanding the nature of each data source is crucial. Once we load these economic indicators from the Federal Reserve economic data, we process each series to ensure they're aligned on a monthly basis. The consolidation step is equally important, as we combine all these process series into a single data frame, ensuring we only keep entries with complete data to avoid any biases or misleading signals in our analysis. Finally, we take a moment to print out the number of rows in our finalized data frame, along with a preview of the first and last few entries. This serves as a sanity check, confirming that our data transformation played out as expected, and allowing us to visualize the trends we're about to analyze further. Looking ahead, the next cell will likely build on these engineered features, perhaps turning our attention toward applying machine learning models to predict economic outcomes based on the signals we've set up. This progression will deepen our understanding of how these features translate into actionable insights in recession modeling. Cell 17. In this cell, we're laying the groundwork for a predictive model that will help us identify potential recessions within a specified time frame, rather than just evaluating the current economic conditions. This concept of forward-looking recession labeling is significant because it shifts our focus from simply observing what's happening now to anticipating future economic trends, which can be crucial for decision-making in finance and policy. The process begins by creating a copy of the original dataset to ensure our transformations do not alter it. We then calculate the yield curve slope by taking the difference between the 10-year and 2-year government bond rates, which serves as a key indicator of economic expectations. Next, we analyze year-over-year growth rates for several economic indicators, including industrial production, retail sales, and the consumer price index, all measured over a 12-month period. These metrics offer insight into growth trends and inflation, both important for understanding economic health. We examine labor market conditions by calculating changes in the unemployment rate over 3 months, alongside the year-over-year changes in unemployment claims. These variables provide a snapshot of shifts in employment, which tend to precede economic downturns. Additionally, we assess monetary policy by measuring changes in the federal funds rate over a 6-month period, reflecting how central bank actions may influence economic conditions. To capture leading behaviors in the data, we introduce lagged versions of these variables, specifically looking back 1 to 12 months. This allows us to model how changes in these metrics can predict future economic states. The resulting feature columns include all these lagged variables, which we carefully select and clean by dropping any rows that contain missing values for these features. As we display the top rows of our modified dataset, we see the structured preparation necessary for our predictive analysis. Looking ahead, the next cell will likely utilize this dataset to implement a model that predicts the likelihood of a recession occurring in the near future, setting the stage for deeper analysis and interpretation of these trends. Cell 18. This cell is focused on a crucial step in our predictive modeling process, creating labels for future recession periods based on historical data and splitting this data into training and testing sets. This not only helps in evaluating the performance of our model, but also sets the stage for understanding how well we can predict economic downturns using logistic regression, a method known for its interpretability and effectiveness. To begin, we define a function that generates labels indicating whether a recession is expected in the upcoming months, based on a series of past recession records. The function examines the next few months of recession data and assigns a label. It sets the label to 1 if a recession is predicted anytime within the specified horizon. This mechanism allows us to translate our historical recession data into actionable labels for our model. Importantly, learners should be aware that when calculating these labels, any edge cases, such as evaluating future months that might exceed our available data, are handled by returning NaN when necessary. Next, the code specifies a horizon for predictions, set to 6 months here, although this can be adjusted based on the specific needs of the analysis. After generating the labels, we drop observations that don't have complete future data available, ensuring that our model is working with high-quality inputs. We then prepare our feature set and the target variable for model training. In the following steps, we split our dataset into training and testing components, using 80% of the data for training and reserving the remaining 20% for evaluation. We create a pipeline that standardizes our feature set and applies the logistic regression model, enabling us to efficiently train on our training data. After fitting the model, we calculate the predicted probabilities for the test set, which provides insights into how likely a recession is predicted according to our model. Finally, we evaluate the model's performance using several metrics, including the ROC-AUC and Breyer score, which are key indicators of classification accuracy. As we wrap up this cell, it's important to note that while logistic regression provides a strong baseline, we will likely explore other models in the upcoming cells to see how they perform in comparison. This ongoing analysis aims to refine our understanding of economic indicators and improve prediction capabilities in future contexts. Cell 19. In this cell, we're taking a significant step toward visualizing the likelihood of upcoming recessions using Plotly. By merging recession probability data with actual historical recession periods, we're able to create a more informative and engaging chart that illustrates trends over time. The first aspect to note is the estimation of recession probabilities derived from our model. Here, we create a pandas series that captures the predicted probabilities of a recession occurring in the upcoming months. This gives us a quantitative measure we can visualize later. We also prepare a data frame that includes both this probability and binary indicators for past recessions, allowing us to see how present predictions align with historical events. Moving into the plotting, we initialize a Plotly figure, where we add a line chart depicting the predicted recession probabilities. This line gives us a clear view of how the forecasted risk changes over time, with the x-axis representing dates and the y-axis illustrating the calculated probabilities. It's important to remember that the accuracy of these probabilities hinges on the model's assumptions and data quality. Any misrepresentation in the input can lead to misleading outputs. To enhance our visualization further, we incorporate recession shading on the chart. This involves identifying periods when recessions occurred and marking these phases distinctly on our graph. We do this by tracking where the recession indicators are true, ensuring we capture all continuous spans of recessionary periods. In practical terms, if we detect that we're currently in a recession and have processed our data correctly, we create shaded rectangles to visually represent these times of economic downturn. The gray shading helps to clarify the relationship between predicted recession probabilities and actual recession durations. As we finalize the layout of our figure, we set engaging titles and axis labels to make the chart user-friendly, adjusting the overall dimensions to ensure clarity. The resulting visualization can be a powerful tool for understanding economic trends at a glance. Looking ahead, the next cell will likely delve into analyzing the implications of these predictions further, perhaps exploring how to leverage this information for decision-making or policy evaluation. This continuity in our analysis will further enhance our understanding of economic indicators and their real-world applications. Cell 20. In this cell, we're diving into the foundational concepts for creating an AI macro agent that interprets economic conditions and adjusts portfolio allocations accordingly. This is significant because connecting macroeconomic data to investment strategies can lead to more informed and effective decision-making. The process outlined here is methodical and sequential, starting with state representation, which forms the basis for how our agent perceives different macroeconomic regimes. Following that, we have regime detection, where the agent identifies the current economic conditions based on historical data. This step is crucial, since different regimes often demand distinct strategies for portfolio management. Next, there's agent interpretation, which focuses on how our AI understands and processes the identified regimes to inform investment choices. This is followed by a reinforcement learning upgrade, allowing our agent to optimize its decisions over time by learning from outcomes. The expected advantage here is that the agent learns not only which macroeconomic conditions are currently at play, but also how to allocate assets most effectively in response. In this setup, we're particularly interested in a few key metrics: the expected return from investments, the potential drawdown during downturns, and overall volatility. These factors create a reward system for the agent, enabling it to refine its strategies based on past performance. By the end of this process, we anticipate generating a monthly label reflecting the current economic regime, a policy that dictates asset allocation based on those labels, and a performance evaluation to visualize action preferences using Plotly. This integration of real-time data and adaptive learning has the potential to enhance investment outcomes significantly. As we move forward to the next cell, we'll likely be implementing more detailed algorithms to analyze the agent's performance and refine its strategies even further. This promises to deepen our understanding of how economic indicators influence investment approaches. Cell 21. In this cell, we're harnessing the power of various economic indicators by pulling macroeconomic data from the Federal Reserve Economic Data, also known as FRED. This data is crucial for analysis because it provides insights into various aspects of the economy, such as unemployment, inflation, and consumer sentiment, which help us understand broader economic trends. The process begins by defining a start date for our data collection, set to January 1st, 2000, and it will continue until the present. We create a dictionary that maps FRED identifiers to more accessible names. This makes it easier to work with the data later on. The function we've defined, toMonthEnd, is designed to aggregate this data, either taking the last observation of the month or averaging values, if that's specified. This is essential when we're dealing with time series data, as it allows us to standardize our measurements to a monthly frequency. Next, a function called loadFred iterates through the identifiers in our dictionary, using the pandas data reader to fetch the desired data for the given date range. Each piece of data is stored in a dictionary, serving as a structured way to keep track of our raw data. After gathering this data, we use pandas concat function to organize these indicators into a cohesive data frame, with each column representing a different economic metric. The columns in our data frame are appropriately named based on the earlier mapping. Importantly, we also drop any rows with missing values to ensure that our final dataset is clean and ready for analysis. As we summarize this process, the resulting data frame contains critical economic indicators that can be analyzed further. As we look ahead, the next cell is likely to build on this foundational data by performing analysis or visualization, helping us to derive meaningful insights and trends from the macroeconomic indicators we've just collected. This will pave the way for deeper economic analysis or predictive modeling in our workflow. Cell 22. In this code cell, we're focusing on engineering key macroeconomic features that will provide an agent with vital insights about the economic environment. By extracting and calculating these features, we can gain a clearer understanding of different economic regimes, such as growth or recession, and how they impact various indicators. This understanding is essential for informed decision-making in both economic modeling and forecasting. The first step in our process is making a copy of the macroeconomic data frame to avoid altering the original data. From this copy, we begin by calculating the yield curve slope, represented as the difference between the 10-year and 2-year government securities rates. This measure helps us assess expectations about future economic activity, with a steeper slope often indicating growth. Next, we delve into year-over-year growth rates for several key indicators: industrial production, retail sales, and consumer price index. These metrics reflect changes in economic activity and price levels over the past year, providing a broader context of trends rather than just point-in-time snapshots. We also look at labor market dynamics by calculating the change in the unemployment rate over 3 months, which allows us to identify short-term trends. Additionally, we measure the year-over-year growth in unemployment claims, highlighting shifts in the job market. To gauge monetary policy changes, we inspect shifts in the federal funds rate over a 6-month span and sentiment changes over 3 months, which offer insights into consumer confidence and potential future spending behaviors. Finally, we select a subset of these engineered features to analyze further, ensuring to drop any rows with missing values to maintain the integrity of our dataset. By examining the tail of this newly created data frame, we can visualize the latest observations of these macroeconomic indicators. Looking ahead, the next cell will likely build upon this foundation by using these features to inform our economic agents analysis, preparing us for deeper exploration into their implications and potential predictions in upcoming tasks. Cell 23. In this code snippet, we are diving into an unsupervised learning approach to identify macroeconomic regimes using Gaussian mixture modeling, specifically through soft clustering. This method is significant because it helps us uncover hidden patterns in the data that may not be immediately obvious, allowing for better insights into economic conditions. First, we set the number of clusters K to 3, but we have the option to try 4 if desired. This flexibility gives us room to explore varying levels of complexity in our analysis. Next, we standardize our feature set by using standard scalar, which transforms our data to have a mean of 0 and a standard deviation of 1. This scaling is crucial, especially in clustering tasks, as it ensures that each feature contributes equally to the distance calculations. Once our data is properly scaled, we initialize the Gaussian mixture model with a specified number of components and fit it to our scaled data. The model assigns each data point to one of the identified clusters or regimes, producing soft classifications that indicate the likelihood of a data point belonging to each regime. We store these regime assignments and also compute the maximum probability for each observation, which helps us gauge the confidence of the model's predictions. To keep our data organized, we create new columns within our feature set that denote the assigned regime and its maximum probability. By adding a date column derived from the index, we enhance the readability of our results. The output shows not only the regime assignments, but also provides a glimpse into the structure of our dataset. Furthermore, we summarize the characteristics of each regime by calculating the mean values of the relevant features for each cluster. This summary table allows us to interpret the clusters easily and identify the distinct economic conditions associated with each regime. It serves as a valuable guide for future analysis and hypothesis generation. Looking ahead, the next cell will likely build upon this foundation by examining how these identified regimes might influence decision-making or forecasting in economic contexts, enriching our understanding of the detected patterns and their practical implications. Cell 24. In this cell, we're pulling in specific investable assets, namely ETFs, and calculating their returns for the next month. This is an essential step for anyone engaged in financial analysis, as understanding the expected performance of different asset classes can significantly inform investment strategies. We begin by defining a list of key assets. SPY represents risk-on equities. IEF serves as intermediate treasuries, which provide a risk-off ballast. SHY reflects short treasuries acting as a cash proxy. And GLD stands for gold, which is often viewed as a diversifier and an inflation hedge. With a clear selection of assets, we move on to download their adjusted closing prices for the specified date range, ensuring we gather only the relevant data. After fetching the data, we perform a resampling operation to align these prices to the end of each month, which simplifies our analyses. We then calculate the monthly returns using the percentage change method, allowing us to see how these assets performed from one month to the next. It's crucial to handle missing data effectively, which is why we remove any rows that have no data after resampling. Next, we align our return data with predefined regime dates. This alignment is important for ensuring that the returns we analyze correspond precisely to the market conditions we're studying. Lastly, we display the dimensions of both the features and returns data, along with some initial rows of these datasets. This gives us a quick glimpse into the data structure we are working with. As we prepare to delve deeper, the next cell will likely leverage this foundational data, perhaps applying analytical techniques or models to better understand the relationships between these assets and the regimes we're studying. Getting this step right will be key to fruitful exploration ahead. Cell 25. In this cell, we are defining a set of portfolio allocation strategies, referred to as actions, which are essential for guiding our investment decisions. Each action represents a distinct allocation style that an agent can adopt based on varying market conditions, reflecting different levels of risk exposure. To break this down, we begin by using a Python feature called a data class to create a blueprint for these actions. The action class includes a name, which helps identify each strategy, and a dictionary called W, where the weights for each asset are specified. This dictionary indicates how much of the total portfolio is allocated to each asset, allowing for nuanced investment strategies that can adapt to changing market dynamics. 3 specific actions are defined: risk on, neutral, and risk off. The risk on action emphasizes a higher allocation to equities, with 80% in the SPY asset, signaling a bullish stance on the market. Conversely, the risk off action takes a defensive posture, favoring safer assets like bonds, with 60% allocated to IEF. The neutral action attempts to balance risk and reward, distributing funds more evenly across both equities and fixed income. By structuring our actions this way, we lay the groundwork for more complex decision-making in our model. It's important to recognize that these allocations can significantly impact overall portfolio performance, and they provide a clear framework for understanding investor behavior in varying market scenarios. As we move forward, the next cell will likely build upon these actions by incorporating them into a broader framework for simulating trading scenarios, helping us to visualize and evaluate how different allocation strategies perform over time. This progression will further enhance our understanding of how to navigate the financial landscape. Cell 26. In this cell, we're diving into the computation of a reward function that will help us assess the performance of a portfolio by factoring in both drawdown and volatility. This is crucial because it allows us to not only understand the returns generated by the portfolio, but also to account for risks associated with losing investments and the fluctuations in their value. We start with the function that calculates the total return for a portfolio based on a set of asset weights and their corresponding monthly returns. It takes in a dictionary of weights and a series of monthly returns, multiplying each asset's return by its weight to find the overall return. This step is essential, as it ensures that we accurately reflect how each asset contributes to the portfolio's performance. Next, we compute the drawdown, which represents the decline from the peak of the portfolio's value. This is done by taking the cumulative maximum of the equity values and determining how far that current equity is from its peak. This measure helps identify how much loss an investor might have experienced from the highest point, adding a critical dimension to risk assessment. The reward function itself then takes into account monthly returns, drawdown, and volatility, with specific weights assigned to each of these components. The deeper the drawdown, the larger the penalty, as we use its absolute value to reflect the seriousness of losses. Similarly, volatility contributes to the overall reward calculation, helping us gauge the risk involved in pursuing higher returns. We've also defined the weights for the penalties associated with drawdown and volatility to provide flexibility in experimentation. For example, you might adjust these parameters based on specific risk tolerances or investment goals. The rolling volatility is estimated over a year, which provides a smoother measure of risk as opposed to focusing on short-term fluctuations. As we proceed to the next cell, you can expect to see this reward function put to use, allowing us to evaluate various portfolios' performance under the criteria we've established. This will help in making informed decisions about asset allocation and risk management strategies moving forward. Cell 27. In this cell, we delve into a class designed for implementing Thompson sampling within different regimes, fundamentally aimed at optimizing decision-making based on observed rewards. This methodology is pivotal in environments where the conditions vary, as it enables adaptive learning about the expected returns of various actions in those different scenarios. The class named Thompson Bandit regime begins by initializing key parameters. It captures the unique regimes and the number of actions available, while also setting up prior beliefs about the mean and variance of expected rewards. Here, the prior is a normal distribution characterized by default values. This is crucial for establishing a baseline from which updates can be made as we gather more data. Within this setup, the code maintains dictionaries for both the mean and variance of expected rewards for each combination of regime and action. As actions are chosen and rewards observed, these statistics evolve, allowing the model to refine its predictions over time. It is important to note the use of a normal posterior, which facilitates efficient Bayesian updates as new information is acquired. When it comes to selecting actions, the sample action method employs Thompson sampling by generating samples from the current belief distributions for each action under the observed regime. The method identifies the action with the highest sample value, thereby allowing the agent to focus on the most promising choices based on its current understanding. The update method is where the magic of learning happens. After observing a reward associated with a specific action in a given regime, the posterior mean and variance are recalibrated. This update mechanism is not just a formality. It plays a significant role in dynamically adjusting to the realities of the environment, capturing the uncertainty in the observations through the noise parameter. As we proceed, keep in mind that this modeling approach relies on sound initial assumptions and consistency in regulating the noise factor. Any inconsistencies can lead to misleading insights. Moving forward, the next cell is likely to build upon this framework, perhaps by incorporating real data observations to see how the learned policies perform in practice, thereby giving us a tangible sense of the efficacy of this adaptive strategy. Cell 28. In this cell, we're running a simulation that implements a walk-forward strategy for a trading system, which is crucial for evaluating performance over time in a dynamic market. The goal is to simulate investment decisions based on changing market regimes and calculate the resulting portfolio returns, equity, drawdown, and volatility, thereby helping us optimize our trading actions. As the simulation runs through a series of time steps, it begins by initializing necessary variables, such as an equity value that starts at 1, and an empty log to track our results. Each iteration of the loop corresponds to a specific date in our dataset, allowing us to adapt the strategy dynamically based on market conditions. Here, we identify the market regime for that date, turning our attention to the bandit algorithm, which samples an action based on the current regime. Using this selected action, we calculate the realized portfolio return for the month, updating our equity accordingly. It's noteworthy how equity reflects cumulative performance, enabling us to monitor how our investment grows or shrinks over time. Equally important is the drawdown, which we compute to identify any declines from our peak equity, crucial for understanding risk. To add further depth, we estimate the rolling volatility of our portfolio returns, which helps gauge risk exposure. This volatility is incorporated into our reward function alongside drawdown data, ensuring that both performance and risk are considered when updating our strategy with the bandit algorithm. After each update, we log detailed information, including date, regime, action taken, realized return, and various metrics associated with our performance. Finally, this log is converted into a data frame for easier analysis and visualization. As we look ahead to the next cell, we can anticipate a deeper exploration of the output data, and perhaps some analysis on how our strategies perform over different market conditions. This will further inform our understanding and guide us in refining our trading approach. Cell 29. In this code cell, we're examining the performance of various investment strategies through a benchmarking approach using static allocations. This is an essential step because it allows us to evaluate how different portfolio weights impact returns over time, helping us understand the effectiveness of our investment decisions. The heart of this implementation is the function called runStatic, which takes a dictionary of weights as its argument. Inside the function, we apply a method to the returns data, retsm, that calculates the portfolio return for each time period by using the specified weights. This is achieved through a lambda function that calls another function, portfolio return, on each row of return data. Once we have the portfolio returns, the cumulative product is computed. This step allows us to track the growth of our investment over the selected period, revealing how the portfolio performs when adhering to these static weights. Next, we see how the function is utilized by invoking it with different sets of weights defined in actions. Each invocation produces a series of cumulative returns that correspond to specific market conditions: EQ risk on, EQ neutral, and EQ risk off. These represent different strategic positions based on market sentiment. We also calculate the cumulative returns for the SPY, which serves as a benchmark for comparison against our portfolio strategies. It's important to be aware that the output of runStatic will only be accurate if the weights are a valid representation of our investment strategy, and each index aligns correctly with the return data. Any mismatches in data can lead to erroneous conclusions about performance. As we proceed to the next cell, we'll likely delve deeper into interpreting these results, drawing comparisons, and understanding how the strategies stack up against each other and against the market benchmark. This will provide us with valuable insights that can inform future investment choices. Cell 30. In this cell, we're creating a visual representation of the macroeconomic regimes over time, specifically focusing on the slope of the yield curve between 10-year and 2-year bonds. This visualization is vital because it helps us understand how different economic conditions relate to changes in interest rates, giving insight into potential future movements in the economy. We begin with a scatter plot that uses Plotly's convenient express module. The x-axis represents dates, while the y-axis shows the yield curve slope, labeled as 10y2y slope. This metric is crucial for evaluating the market's expectations about future inflation and economic growth. Each point in the scatter plot is colored by the regime, indicating the different economic phases identified in our analysis. This visual differentiation allows us to observe how these regimes correspond to variations in the yield curve slope over time. It's important to note the assumptions behind our model, particularly in how we define the regime variable. Mislabeling or oversimplifying these regimes can lead to misleading interpretations of the yield curve. Additionally, one should be cautious about reading too much into short-term fluctuations. Trends often provide a more accurate picture of underlying economic behavior. After setting up the figure's dimensions for clarity, we render the chart to visually communicate this complex information. This not only enhances our understanding of the economic environment, but also serves as a backdrop for deeper discussions about monetary policy and its impacts on the financial markets. As we look to the next cell, we might delve deeper into interpreting these regimes, correlating them with other economic data, or perhaps exploring further visualizations that can refine our understanding of macroeconomic trends. Cell 31. In this section, we're visualizing the choices made by our macro agent over time, specifically focusing on how those decisions relate to different market regimes. Understanding this visualization is crucial because it can help us identify patterns in the agent's behavior depending on varying market conditions. The core of this code snippet leverages Plotly Express to create a scatter plot that effectively displays the agent's actions across different dates and regimes. The res.resetIndex function serves to prepare our data, so we're looking at a fresh index suitable for plotting. The x-axis represents time, with dates indicating when decisions were made, while the y-axis shows the state of the market regime. By coloring the scatter points based on the agent's actions, we can easily see how these choices evolve in different contexts. One of the key aspects to note here is the title of the plot, which informs viewers that this is a time-based visualization of decisions filtered by regime. This sets the stage for interpreting the relationships between action choices and various market conditions. The layout adjustments are made to enhance visibility, ensuring the chart is appropriately sized for better clarity. When interpreting these results, learners should keep in mind that the effectiveness of our agent's decisions may involve some assumptions about market behavior and categorization of regimes. If the regimes are not accurately categorized, it could lead to misinterpretations of the agent's actions over time. Looking ahead, this analysis lays the groundwork for deeper exploration into how specific strategies might be shaped by historical decisions. In the next cell, we will likely delve into more quantitative insights, possibly investigating the outcomes associated with these choices. Cell 32. In this cell, we're diving into a comparison of the performance of different trading strategies, particularly focusing on our agent's performance against some static policy approaches and the SPY benchmark. This analysis is crucial because it helps us understand how our model stacks up against established strategies, informing us about its effectiveness and potential areas of improvement. The first step here involves creating a data frame that consolidates the performance data. We have several strategies lined up: the agent's performance, labeled simply as agent, along with various static strategies such as static risk on, static neutral, and static risk off. We also include the performance of the SPY, which serves as a commonly accepted benchmark for equity performance. By organizing this data within a single data frame, we set up the framework for a clear visual comparison. Next, we use Plotly Express to create a line plot that visualizes these performance metrics over time. The reset index method is employed here to ensure that the dates are preserved and correctly formatted for plotting. By melting the data frame, we're reshaping the data so that it can be visualized in a way that highlights the variations in equity curves across our strategies. Each strategy will have its own line on the graph, providing a clear visual representation of how each performed relative to the others over the same time frame. It's important to consider that the visual output allows for a quick assessment of strengths and weaknesses among the strategies. A learner should note that while the graph is informative, it doesn't tell the whole story behind the performance metrics. Understanding the context and decision-making processes behind each strategy is vital. Looking ahead, the next cell will likely expand on these findings, perhaps by delving into performance metrics or conducting a deeper analysis of why one strategy may have outperformed another. This transition will help us tether our insights directly to actionable takeaways. Cell 33. In this cell, we're creating a heat map that visualizes the expected rewards associated with different actions across various regimes. This visualization is crucial because it allows us to see how the best action changes depending on the current regime, providing insight into the effectiveness of our decision-making strategies. The workflow starts by initializing an empty list to collect data. We then iterate through each unique regime found in our dataset, and for every regime, we look at each action available. Here we gather essential data, such as the regime, the action name, and the mean and variance of rewards associated with each action in that regime. The mean reward reflects our expectation of the reward that will come from each action, while the variance gives us an idea of the reliability of that expectation. As we append this information to our list, we structure it as a dictionary for easy access later. After collecting all the necessary data, we convert this list into a pandas data frame, which organizes our data neatly and makes it straightforward to work with for visualization. Next, we use Plotly Express to create the heat map itself. We pivot the data frame to arrange the data so that regimes appear on one axis and actions on the other, with the learned expected reward represented as color intensities. This heat map serves as a powerful tool to identify patterns and make informed decisions based on our model's learnings. We set the aspect ratio and specify the dimensions of the plot to ensure it's clear and easy to interpret. Once displayed, this visualization helps us grasp the relationship between actions and their expected rewards over different regimes. As we look ahead to the next cell, it will likely build upon these insights, perhaps by taking a deeper dive into how to select the best actions based on this information, or by analyzing the performance metrics derived from the identified strategies. Cell 34. In this cell, we're diving into the interpretation of our model's outputs, which is crucial for understanding how our economic framework functions. Here, we're employing a regime model using Generalized Method of Moments, or GMM, which transforms various macroeconomic conditions into distinct states. This transformation matters because acknowledging different economic environments helps us make more informed investment decisions. As we explore the logic, we're essentially facilitating an AI macro agent, which learns to recognize the optimal portfolio allocations corresponding to these varied macro regimes. The beauty of this approach lies in its adaptability. The agent isn't just following fixed rules, but is actively learning which actions lead to the best risk-adjusted returns across different states. The reward structure is quite interesting here. It consists of three critical components: the return, the drawdown, and volatility. Effectively, the agent aims to maximize returns while minimizing both drawdowns and volatility. This means that any strategy that might promise high returns but also carries the risk of significant losses or unpredictable performance will be discouraged. This design encourages the development of more robust, stable investment strategies, which is a key factor in successful portfolio management. It's also important to keep in mind that this methodology rests on certain assumptions about market behavior and the nature of the data inputs we're using. For instance, if the underlying economic indicators don't accurately reflect the true market conditions, the agent's learning and subsequent decisions may lead to suboptimal outcomes. Looking ahead, the next cell is likely to build upon the insights gained from this model interpretation, perhaps by applying this learned knowledge to real-world portfolio optimization or risk management strategies. This progression will deepen our understanding of how our AI agent's findings can be harnessed practically, further bridging theory and application in economics and finance. Cell 35. In this cell, we're exploring the foundational concepts necessary for understanding our recession probability model. This phase is critical as it identifies key economic indicators that have historically proven to be strong predictors of recessions. By examining these indicators, we can create a framework that helps us assess the likelihood of an economic downturn, which can be invaluable for policymakers, investors, and businesses. The first indicator we look at is the yield curve spread, which represents the difference between long-term and short-term interest rates. An inverted yield curve, where short-term rates exceed long-term rates, has often preceded recessions, signaling investor pessimism about future growth. Next, we analyze the unemployment trend. A rising unemployment rate typically indicates weakening economic conditions, while a falling rate can imply economic strength. Another critical measure is jobless claims. An increase in initial claims often suggests a cooling job market, which can be an early warning sign of impending recession. Industrial production, which measures the output of factories, mines, and utilities, serves as a gauge of economic activity. A downward trend in industrial production can reflect decreased demand and reduced economic vigor. Lastly, consumer sentiment captures the overall confidence consumers feel about the economy. When consumers are optimistic, they are more likely to spend, stimulating growth, while a decline in sentiment can foreshadow reduced spending and strain on the economy. Each of these indicators plays a significant role in our recession probability assessment, and understanding their interplay is essential for drawing insights. As we move forward, the next cell will likely delve deeper into the methodologies for quantifying these indicators and how they contribute to our predictive model. Cell 36. This cell introduces key concepts related to predicting housing demand, an essential aspect of understanding market trends. Recognizing the elements that drive housing demand can help us make informed forecasts and decisions in real estate, economics, and policymaking. The cell highlights several primary drivers of housing demand, which include mortgage rates, income growth, employment levels, shelter inflation, as measured by the Consumer Price Index, and consumer confidence. Each of these factors plays a crucial role in shaping the housing market. For instance, changes in mortgage rates can significantly affect affordability. As rates rise, purchasing a home may become less attainable for many people. Income growth is equally essential, as higher incomes generally lead to increased purchasing power and the ability to invest in housing. Employment is another vital aspect. Stable jobs allow individuals to consider homeownership more seriously. If people are worried about their job security, or if unemployment rises, housing demand often diminishes. Likewise, CPI shelter inflation provides insight into how housing prices are evolving over time, which can influence potential buyers' decisions. Finally, consumer confidence acts as an umbrella metric that reflects people's general feelings about the economy, directly impacting their willingness to make significant purchases like homes. As we consider these variables in predicting housing demand, it becomes clear that they are interrelated and can fluctuate based on broader economic conditions. Understanding these connections is critical for anyone looking to analyze or operate within the housing market. Moving forward, the next cell will likely delve deeper into these factors, perhaps by exploring their historical data and how they interact to create trends in housing demand over time. This will equip us with the tools needed for more sophisticated analyses and predictions. Cell 37. In this cell, we're diving into the structured workflow that underpins economic forecasting at major organizations. Understanding this process is essential because it reveals how data is transformed into actionable insights that drive critical business decisions. The first step is to gather raw economic data, which serves as the foundation for all subsequent analyses. From there, we pull in specific indicators from the Federal Reserve economic data, often referred to as FRED indicators. These indicators provide valuable information on things like inflation, employment rates, and consumer spending, all of which are crucial for a robust economic analysis. Next, we focus on monthly alignment, ensuring that our data is consistently tracked and compared over time so that patterns can emerge. This step is vital for recognizing trends and anomalies. Once we have a coherent dataset, we move into feature engineering. Here, we extract and create relevant features that will enable our models to capture the intricacies of economic behavior more effectively. As we progress, these engineered features feed into business and machine learning models, where the real magic happens. This is where predictive models are developed, allowing enterprises to forecast future economic conditions based on what the data tells us. The output here is not just numbers, it's a narrative about potential future scenarios shaped by current trends. However, it's important for learners to be aware of potential pitfalls. For example, misalignment in monthly data could lead to skewed analyses, and the quality of the indicators selected directly impacts the reliability of the models developed. As we transition to the next cell, we'll likely explore specific modeling techniques employed in this framework, highlighting how these methods can enhance our predictive capabilities and inform key strategic decisions in business contexts. Cell 38. In this cell, we are signaling the conclusion of our current analysis. It's essential to have a clear endpoint to summarize the insights we've gained and possibly set the stage for the next steps in our work. As we wrap up, it's a good opportunity to reflect on everything we've learned so far. Each previous cell contributed to our understanding and built a narrative that has led us to this conclusion. Whether we've been exploring data, generating visualizations, or running statistical tests, each step has been tied together with a common goal. Additionally, it's important to consider the implications of our findings, including any limitations or areas for further exploration. Recognizing where we stand now will help inform what we might pursue next. Lastly, this closing point serves as a springboard for the next cell. It will likely dive deeper into those implications or explore new avenues based on the conclusions we've drawn here. As we move ahead, we'll continue to build on our foundation of knowledge, potentially expanding our analysis or integrating new data sources to enhance our findings. With that said, let's carry the insights we've gained into our upcoming work. It's always exciting to see how the narrative evolves.